A heap is a complete binary tree where the parent is always smaller than or equal to its children in a min heap, or larger in a max heap. So the root is the minimum or maximum. We store the heap in an array, which gives us push and pop in logarithmic time and peak in constant time. In the real world, heaps are used for task scheduling, hospital triage by priority, merging sorted logs from many servers, and shortest path algorithms like Dijkstra. This is a min heap. Every parent is less than or equal to its children, so the root is the minimum. We store the heap in an array. The root is at index 0. For index I, the left child is at 2i plus 1, the right at 2i plus 2, and the parent is at I minus 1 over 2, integer division. No pointers, the structure is implicit. In a max heap, every parent is greater than or equal to its children, so the root is the maximum. Same array layout and formulas, only the ordering rule changes. We allocate an array with a fixed capacity, the maximum number of elements. The heap size is how many elements are currently in the heap. It starts at 0 and we update it on every push and pop. The last element is always at index size -1. We add the new element at the end of the array. Then we bubble up. If it's smaller than its parent, we swap. To push, we add at the end and repeatedly swap with the parent until the heap property is restored. We return the minimum at the root. Then we move the last element to the root and remove the last slot. We put the last element at the root and remove the last slot. Then we bubble down, swap with the smaller child until the heap property holds. To pop, we take the root, put the last element at the root, then repeatedly swap with the smaller child until the heap is valid again. We start at the last non-leaf and bubble down at each node. Parent 8 is greater than child 2, so we swap, bubble down with the smaller child. Push and pop are logarithmic because we only follow one path up or down the tree. The height is log n, peak is constant time since the root is at index 0. Building a heap from n elements is linear time. We bubble down from the last non-leaf to the root, and the total work sums to O of n. Space is linear for the array. Index helpers. Parent of I is I minus 1 integer divide 2, left child is 2i plus 1, right child is 2i plus 2. Push, append the new element at the end, then bubble up from the last index. Bubble up, while the node has a parent and is smaller than the parent, swap with the parent and move up. Pop, save the root as min, swap root with the last element, remove the last and decrease size. If the heap is not empty, bubble down from the root. Return min bubble down, while the node has a smaller child, swap with that child and move down. Build heap, from the last non-leaf index, n over 2-1, down to 0, call bubble down at each index. The whole array becomes a heap in linear time.